Hello class, this is CIS170 Operating System Concepts. My name is Glenn Sheneman and I will be your instructor throughout this 8-week ADP course. First thing I'd like to do is get to know the class. So for the on-ground students, I'm just going to pause the video in a second here and have everybody go around and introduce themselves so I can get to know you better and you all can get to know each other better as well. For the online students, I would like you to write a forum post, and I would like one response to that forum post in e-learning. For week 1, you will see this. This is for online students only. It's very clearly identified. So if you have any questions, let me know. But if not, I'm going to go ahead and do the Meet the Class section now. Thank you. Now we'll continue with an introduction. An operating system is a program that manages the computer's hardware as well as its basic functions. And operating systems at their core perform basic computer tasks. So what are some of these tasks? There's the task of the operating system, there's recognizing and installing peripheral devices, managing files and folders. You have to look at the sharing out of memory. You have to talk about the handles and error alerts. We're going to talk about how it manages system security and how it allows software to communicate with the hardware. We're going to understand how it moves data from the hard disk to and from the hard disk, and that it loads and runs other software applications. And last but certainly not least, it handles inputs and outputs. So all of these items here are the tasks of pretty much every operating system, and we're going to focus on different tasks of the operating systems as the weeks proceed here in this class. Thank you. So to continue the introduction, operating systems are designed to be convenient or efficient or a combination of both. So that's an interesting thought. So what that means is that some operating systems are convenient, meaning they're super easy to use. They've got a lot of extended features that you wouldn't necessarily need, but it's very convenient and easy to use. That's the concept behind the Windows operating system, or even the graphical user interface in OS X. So I'd like you to review computer security, identify input and output devices. And we need to understand that operating systems are large and complex. So at this point now, I believe I'm going to have the online students write another forum post identifying input and output devices on a computer. So when you look at things like a printer now, for example, be careful, because a printer can be an input device because it can send a message to the computer saying, hey, I'm out of paper, hey, I'm offline, I'm out of toner. So it can be an input device, but it can also be an output device, and it's an output device when it sends a report to the printer. So I'd like you to put some thought to that. Obviously there's the keyboard, the mouse, there's this microphone that I'm using right now, so all kinds of stuff. But I'd like you to write a forum post identifying quite a few pieces of input and output devices, and that will be in e-learning as well. So to continue on, a computer system consists of 4 primary components. There's hardware. They all have an operating system. They all have application programs, and computers need users, whether it's a single user or many user. So operating systems, it's important to understand that they provide the environment. So we'll continue on. So there's the user view, and this is the way the user sees the computer. It could be a smartphone, it could be a workstation, it might be an old banking terminal. So it could be all kinds of different views, and the operating system maintains and manages those views. Next we'll discuss the system view. This is how the computer sees the computer system. And for the operating system, resource allocation is essential. It's one of its primary responsibilities. So it allocates and maintains computer resources. Some of these resources include CPU time, memory available, file storage space, and then there's other I/O devices. So the CPU time is the amount of cycles or the amount of processing time that the CPU has to handle a certain task or process or job. So when you see your computer sitting there hanging really bad, and it doesn't seem like it's working or anything, that's because there isn't a lot of resources available in regards to its CPU time. Memory available, after a while you can get the same kind of issue with memory when you don't have any available random access memory. You have file storage, resource allocation. That's really talking about your disk drives, whether they're network drives or whether they're local disk drives. And then there's other I/O devices. That could be things like your keyboard, your mouse. You were writing a forum post on that, and we've probably discussed that by now in the on-ground class. So now we'll talk about control programs. They handle the execution of application programs to prevent errors and improper use of the system. So devices such as printers and keyboards are controlled by device drivers. So we're going to be discussing that in Windows, and you will see some of these device drivers when we go through Linux as well. With device drivers, we're primarily going to focus on Windows. It's a little more graphical. If you're going to be using a school's computer for this, the access to the device drivers will be somewhat limited, but we will discuss them, and we will point out where these device drivers are located and how they operate. This is going to be a very hands-on class. So control programs also manage system usage and application programs. So now we need to define operating systems. So there is no true adequate definitions. Different operating systems do different things. Operating systems create usable computing systems. A computer without an operating system won't do anything at all. It'll just come on, and you've actually maybe seen that before. If you don't have anything to boot to on a disk or something, it'll just say not found, and that'll be just about it. There's many different vendor packages that deliver many different operating systems. There's commercial products such as Microsoft. They deliver Windows 10. They also deliver Server 2012. They deliver Server 2008, as well as a bunch of other smaller bundled up operating systems. So Microsoft is a commercial operating system vendor. Then there's going to be other types like Solaris Unix, maybe AIX by IBM. That's a version of Unix. So those are also proprietary and commercial products. And then there's also commercial versions of Linux out there, and there's free and public supported version of Linux. So Linux is open source, and that's the main thing to remember here, where Microsoft is not. You do not get to see the code that Microsoft provides, where with Linux you get to see absolutely all of the code that they provide. So operating systems, maybe we could define it as a necessary program that always runs on the computer. And this necessary program is referred to the kernel. Now there's a lot of programs that assist the kernel, but the kernel is the main operating system program, and that frequently gets updated, and when it does, it's a big undertaking. So we'll look at computer system structure. So most modern computers have the following: one or more CPU. When you hear of a core, that's a CPU. Device controllers. We've talked about the controllers for the devices. There's the bus. That's the channel that controls all the traffic between the different devices and the input and output devices, and as well as RAM, as well as the CPU. And then there's shared memory, which consists of RAM and ROM. So RAM is read-only memory, or I'm sorry, ROM is read-only memory, which means that what's in ROM can only be read. You can't write to ROM. That's not 100% true, but for the most part, a ROM is set in stone. Where random access memory, if you turn your computer off, it goes away. It's totally random memory. Thank you. Now we're going to go through the various parts of the computer system to kind of go over what we discussed on the last slide a little more. So you have your memory, whether it's read-only memory or ROM, or random access memory, which, like we said, that's memory that's volatile, and ROM is non-volatile, which means when you shut the computer off, the memory that's in RAM will go away. Some operating systems run out of ROM. For example, if you remember the Commodore 64, it had an operating system available to it within 5 seconds after you turned the computer on, and that's because the entire operating system for the Commodore 64 was stored in ROM. Whereas with a Windows system, everything gets loaded into memory when the computer is turned on. The operating system is stored on a disk and then gets loaded into RAM, and that's how the computer's controlled. The CPU handles the instructions that are provided by the RAM or the ROM, and it will read from the disk controllers, which control the disks. It may read or send output to USB controllers or the graphics adapter as well. So your graphics adapter is a device driver, and it controls the monitor. So in most cases, monitors are really going to be only output devices. And a keyboard is pretty much always going to be an input device, and disks can be input or output. So this is a basic general picture of how your computer looks, and I believe in Professor Concepcion's class they went over this a little bit, which I believe is a prerequisite for this class. So you should have an understanding from your Intro to Computers course explaining how the computer works, and as computer professionals this is something you should know. So now we'll go on and we'll discuss the Bootstrap program. This is stored in the EEPROM, which is a firmware or ROM. We'll just call it ROM for simplicity's sake right here. A Bootstrap program is the program that starts up when the computer is turned on. So on a ROM for a PC, you start it up, it's going to have some settings that you can configure, and it's going to say, this is where the disk drives are. This is what I want you to start first. And then the disk drive itself will have its own Bootstrap on it, which will know where the kernel is for the operating system and know where to go get it and know where to start it up. So once the kernel is loaded, then other system processes and helper programs will work along with the kernel. So these are referred to as processes or daemons, and we can see a lot of those as we go ahead. So if you don't fully understand this yet, don't worry, we will discuss it more as we go through our hands-on work, which is how I prefer to operate anyway. But that's an important thing to remember. So now we're going to talk about interrupts. There's hardware interrupts, which are examples such as the printer running out of paper, a mouse click, a hard disk signaling that it has read or written data, a network device signals that it may have received packets or sent packets. So these are physical hardware occurrences that trigger interrupts, where software interrupts are triggered by system calls or software for the most part. So when a program ends, you end Microsoft Word, it sends an interrupt to the operating system saying, hey, Word has ended. Same thing with starting Word or any other program. If you wanted to open a file in Word, that would trigger a software interrupt as well. So just keep in mind I was using Word as an example, but it's going to be with any type of software that's run. It can trigger a software interrupt.
Alright everybody, so now I'm going to go ahead and show you what the BIOS on my PC here is like. My computer's turned off right now, I'm about to turn it on. And it's going to bring up the big splash screen, which I actually just enabled, and it's going to tell me I need to hit delete to access my BIOS. Different machines and different BIOSes have different settings. So now I'm in my BIOS. Right along here you can see my cursor. Right along here, these are the different boot orders of how the system will boot and where it looks for the operating system specifically. So it's looking for something that will boot, and usually what boots is going to be the operating system, or it will at least have a pointer to the operating system. So let's take a look at the settings now. Let's take a look at the system status. Oops, I went into advanced on accident. Let's take a look at system status. It's going to tell me my BIOS version right there. It's going to give me some system information. It's going to tell me how much physical memory I have. So when it says physical memory, that means RAM or random access memory. It's going to have the memory cache, which is 1 megabit. And we can look at some system manufacturer information. This vendor did not complete too much of this. We could actually fill this out ourselves, but I don't have too much concern about that. Over here we've got overclock settings, which can really make your CPU heat up, and it can really shorten the life of your machine. So I try not to overclock my systems, and there's really no reason to. If we go in to the boot order here, we can see that it's not actually finding my hard drive where my Windows is installed until boot option 10. It's trying to use its various USB and CD, DVD, ROM options first. So I think that's kind of interesting to point out. If I go on and look at security here, I can set a password. I can look to see if somebody has tampered with the system. At this point, I don't have a password set. I'm really the only person who can get at this computer to toggle with that stuff. So a lot of good information there. You can see the USB configuration, the different power management settings. You can tell this is an older machine because it's set for Windows 8.1. Wake up on event settings, that's something that's a little bit interesting. So this is all disabled right now, but I could get the computer to wake up if it was shut off based on different computer settings. Here it shows I've got a Core i5 CPU, and it operates at a clock speed of 3.5 gigahertz. This is a much older computer, but it works really, really well, and I'm really happy with it. So I don't want to get rid of it anytime soon. I'm happy with it still. So you don't always get lucky with your machine, but I believe I did here. So I'm hitting escape, and I'm going to exit without saving because I don't want to change anything.
And lastly, this week we'll discuss the timer. So timers are used in operating systems to ensure the control of the CPU is maintained. This prevents programs from getting stuck in an infinite loop and just running out there for hours and hours, or forever actually, without ever stopping. Timers can be variable or fixed, which means you can either set the timers and have it be programmed something you specify, or it can be a fixed setting. An example of a timer that I like is when you have a program in Windows, which I know we all have, that's been hanging out there. After a minute or so, it'll pop up on the screen. It'll say in the menu bar, it'll have the name of the program. It'll say not responding next to it. And then shortly after, you have the option to terminate or to continue. So these kind of things are useful to make sure that the program actually is stoppable and that it doesn't just run forever. So timers control that sort of thing. Hopefully that makes some sense to you. Thank you.
Discuss the different types of processor usage. Back in the early days, computers really came with one central processor or CPU. CPU stands for Central Processing Unit. As time went on, people realized that they needed more processing power, so manufacturers such as Intel and AMD made chips larger and larger and more powerful. However, over time, they started to realize that the more powerful they made these big chips, the more heat that they used to use. I don't know if any of you remember back in the Pentium 2 days, but they had huge fans that they were using to cool the Pentium 2 processors. And the amount of heat generated would make these large processors unreliable to a degree, and it would make them very power inefficient to run. So over time, they decided to, the manufacturers being they, decided to come up with multiple CPUs on one processor or multiple CPUs, period. And we began referring to CPUs as cores interchangeably. So a core is basically a microprocessor that exists on a chip. So one CPU chip can have more than one processor on it. So when you hear about a 4-core machine or a 6-core machine, that means that they have 7 processors on that chip. So, or they have 7 processors depending on how it's configured. So let's compare. So that sounds like a great answer for everything. And yes and no. So let's take the picture on the screen here now. We have over on this side here, we have a program that, let's say, draws a picture. These periods here represent pixels, okay? So now we have the red and the black, okay? So, or actually that looks like blue. So let's say that the pixels are going to get drawn on the screen, and we're going to use multiple processors to do it. Okay, so the CPU might divide up the work where this right here, these pixels all get processed and handled by the second CPU, while these pixels here get managed by the first CPU. So the picture is rendered on the screen with two CPUs, each of them doing work. This is a very, very good example of multi-core processors being useful. So when you're looking at video games, I know a lot of you probably play Fortnite and what have you out there. So the multiple CPU model is very good. You also want these CPUs to be somewhat quick, but this is a good example. When you're dealing with graphics and video, things to that nature, having multiple CPUs is very beneficial. However, let's say you have a program that's going to prompt for input and display a message. Like, let's say the program says, "What is your name?" It prompts you for input, and then it's going to spit out hello and then your name. So in this case, the CPU is going to, let's say CPU 1 is going to run these steps here. It's going to sit there prompting for your name. It's waiting for you to type something, and you may think you responded to that the second it comes on the screen, but the lag that you see in the microprocessor can be extreme. Like 1 millisecond is a ton of time to one of these processors. So in an instance like this, if these are the types of applications you're running, there's really no point in having a multi-core processor. So multi-core processors are useful depending on what you're trying to do. Thank you very much. To show you an example of a cache, and I'd like to discuss that with you. So we'll go into Google here, and we'll type, "What is a cache?" And from the first one, there's searchstorage.techtarget.com. There's the definition of cache right here. You can see that as I'm doing this, this is my browser cache right here. I'll show you in Firefox how you can get to this. So if we click on this link here, we can see that a cache, pronounced cache, is hardware or software that is used to store something, usually data, temporarily in a computing environment. So this data is not meant to be kept. This data in here represents files, it represents JavaScript, it can represent cookies. It's all stored with these strange GUIDs so that you don't know what it is without really digging into it. It's a little extra layer of protection there. But the information is readily accessible, and this is stored, so next time I come to this page, some of this information will already be here, such as these little images here of the Twitter and what have you. It's probably one of these files. So what I'd like to do now is I'd like to go in to history. I'd like to clear recent history. I'd like to clear the cache, the cookies, the logins, and everything. And watch over here, because it's going to get rid of everything once I clear that cache. I could clear the cache for just one day or several days. Doesn't really matter. So now that I'm back here again, I have everything in its default state because everything's been cleared out of here. As you can see, something was recreated from going to this site right here. It's probably coming from this Google search window. So here I can go back and do something again. Let's say I want to go to youtube.com. I bring up YouTube. I do in Google. It gives me the link there. I typed it in the wrong spot, it looks like. I click there. I'm on YouTube, and it's all kinds of additional additional information in the cache. So that's an example of how a browser cache works. I'm not going to really focus too much on this. If you wanted to see your cache information in Firefox, you would type about and then cache. Spell it, cache. And this is what we're looking at right here. This is my disk cache right here, and I could list these entries and get the same information here. It just kind of translates it a little bit better for you. So inside of this here, I can see what's going on. It's got the file sizes. It shows the stamps of when it was added, modified.
As we previously discussed, secondary storage is storage outside of memory. This can be PDA storage, it can be flash drive storage, it could be hard disk drive storage, it could be network disk drive storage, and nowadays it can even be cloud storage, which we've discussed. So secondary storage is storage that is outside the memory of the computer. So usually that's something that we see and hear about on your computer's hard drive. And hard drives are broken down by file systems. So different types of operating systems use different types of operating systems, but there is some compatibility there. For the next slide here, I'm going to continue on to this site here, How to Geek. So this is the URL that you can reference and read for yourself. This is a really good website for general information and troubleshooting. I find myself coming to How to Geek quite a bit. So let's talk about the FAT32 file system first. So this is a Windows file system. It's an older file system. There was a FAT16 file system even before that. So it was used up until Windows XP. A lot of smaller devices like your flash drives and your storage drives will still use that nowadays. I will go ahead and insert a flash drive in here right now. This is one of them that Albertus likes to give you when you register for classes. It's a smaller drive, but I'll put it in right now and we'll show you how we see that here in just a second. Next we have the NTFS drive. So when you put your Windows XP, your Windows 7, your Windows 8, 8.1, your Windows servers, all modern Windows versions use NTFS for the file system. External drives can be formatted either way, but NTFS is more reliable. It's more stable than the older FAT32 file systems, and it's used with larger disk drives now. So the HFS file system is what's used by Macs. It's pretty much used to format all their computers and stuff like that. Macs, however, are also able to read FAT32 file systems, although they can only read the NTFS by default. So a lot of third-party software and vendor support is needed with the HFS and the Mac file systems. They're not too compatible, but pretty much everything seems to be compatible with FAT32 for external drives. The ext1, ext2, ext3, and ext4 are Linux-based file systems. Nowadays, the ext4 is the standard. I believe it stands for Extended File System, and it doesn't like to read well with Windows and what have you. However, Linux will read any file system pretty much that's a Windows-based file system. For that reason, a lot of times when you format an external device on a Linux machine, it's still recommended that you use FAT32. So this BTRFS file system, we're not going to be working with this. It's still mostly in development right now. So here they're calling swap a file system, but I don't even really know why this is on here. This is really, a swap file in Linux is the same thing as a page file in Windows, and it's really just a dedicated partition regardless of whether you're using Linux or whether you're using Windows. So I don't even know why this is here. I don't actually want to go into this right now. I'll do that later on. But going through it real quick, FAT32 is an older Windows file system. NTFS is a modern Windows file system. HFS Plus is the Mac file system. ext4 is the current Linux file system that we use, and this is a development Linux file system. I've never actually seen one of these. So we're going to go on in just a second to the Linux directory structure, and I'll lecture on that in just a minute. Thank you very much. So why don't we take a look at the Windows Explorer before we go ahead and look at the Linux folders. So right here, when you click on this PC, it will give you a good overview of what your Windows folders and your devices look like. So that being said, as you can see right now, it's showing that I only have a C drive and a D drive, which the D drive is a DVD drive. I know for sure I don't have a DVD in this machine, but if I take that jump drive, that Alberta's flash drive that I was talking about, and I put that into my computer, all of a sudden I have an E drive, which unfortunately there's absolutely nothing at all on this disk, but it has its own root right there. As you can see, that's E with the backslash, the Windows backslash. And if I were to go back to look at my PC view, I could also look at my C drive here, and it has its files on it here. Okay, so going back to the PC view for 1 second, I did want to demonstrate that if I go into properties, it's a FAT32 file system. So like we were discussing previously, the FAT32 file system is tied to smaller flash drives and USB jump drives and what have you. The local C drive is actually internal inside my computer. It's a much larger drive. It's almost 1 terabyte. So if I look at the properties for it, it's an NTFS drive, which most C drives on your computer will be NTFS if they're newer machines. So I wanted to bring that up. Now we'll go through and we'll look here. So this is the root of the C drive right here. Okay, so it's designated just like that. So C colon with the backslash, that shows the root of C. So program files is an important directory. It shows all of your files that and all of your programs that you run that are 64-bit programs. So all of these programs here are 64-bit programs that I'm running on this machine. The 32-bit programs are under the program files x86 directory. Okay, so these programs in here are all going to be 32-bit programs that are running. Program data, these just break up into folders. It stores a lot of system-wide program data for different things that get opened and different programs that get used. The user directory, we'll look here at user public because it's a much more broken down view. And because it's public, it's going to say public in front of these, but this is actually going to be just the desktop directory, the document directory, the download, the music, the pictures, and the video directories. These are pretty much set up by default with most Windows systems, so if I were to go ahead and look at my own folder here, I have a few other items in there, but again I have desktop, downloads, documents, videos, and so on and so on. So going back, then you have your Windows directory, and this is where your actual operating system exists. This is where all the libraries that support it and the kernel itself are located. So good directories to look at here are the fonts directory that stores all the different fonts that your computer will use. You can go down, you've got the system, where somewhere you have the system and the system32 directories. Those store all your drivers, your device drivers, and your program drivers. And if you go into system32 under drivers, you'll have an etc directory, which stores the host file and your services file, and we're going to go into that in Windows, and we're going to go into that in our Linux Unix environments. So those are just an example of some of the file systems that are important in Windows. Thank you very much. This on the next set of slides, so this will make much more sense in just a minute. So now if you all remember from our Windows discussion we had a few minutes ago, they can have a root of the D drive, the root of the E drive, the root of the C drive, the root of any network drive. So there can be many different roots and many different types of file systems that all connect in to a Windows environment, and there's separate drives, and you can actually see the drives very clearly and very simply on a Windows computers, because the drives are usually designated by a drive letter, and it's usually really obvious. It doesn't work that way in Linux. Every folder you have in Linux is based off the root, and the root is a simple slash that looks like this right here. So on a Linux computer, everything is at the base level off of the root. So you'll have separate drives that get mounted up, but they get mounted up, and I will go through that in just a second here. So under the root directory, you have the bin directory. That's where the user binaries are contained. These binaries are programs that can run and that are useful to the user. Under sbin is where the system binaries are going to be located, which are the system programs and the system commands. These will be used when you're doing administration on the server itself. All of the configurations for all of the different applications that are configured on a Linux machine are primarily stored under the etc directory, and that's pronounced etc. So this will have all your services that are running. It'll have every different type of application that you might have installed. So for example, your web server, if you're running your Linux machine as a web server, your web server configurations will be under this folder. So all your configurations are contained under etc. Then there's the process information folder and directory. So there's not going to be any time that you're really ever going to use this. It stores your various processes as they're running. Okay? Then there's the var files. That's where your variable information is contained. So for you, going back to the website example, your configuration for your website will be contained here, but your actual website files will be located under var. So on a Linux machine, for the most part, var www is going to be your web server. You'll also have your login files, which are stored under var for the most part. So a lot of work gets done under var. It's an important folder. There's also the TMP folder. This is the temporary files folder. This is where temp files get created and stored. This can get blown out really easily, and you should never put anything under temp that you don't expect to lose at some point. So user programs. So when a user writes a program and the user does some development, has a CGI script that they're using with their website or what have you, it's best practice to put it under the user folder. Now the home directories, with the exception of the root home directory, they're stored under here. In this class, you're all going to have logins to my Raspberry Pi to do your work in. Your logins will be under the home directory here, and you'll see that very shortly. So the bootstrap and the bootloader programs are often kept under the boot directory. The system libraries and the system source code in Linux and what have you, you might have your C program libraries, you might have some Java libraries, but your library and your system information stuff is going to be stored under the lib folder, which stands for libraries. Any kind of an optional add-on is going to be under OPT. I see more OPT folders and files being used on Unix systems than I do with Linux. That's just an observation. The mount directory. So if you were going to mount a separate drive on your computer, like you wanted to mount up a CD so you can read something off of a CD, or you wanted to mount up a DVD, or you wanted to mount up a flash drive or something, usually they get mounted under here. So like I said, you won't see a separate drive letter or anything like that. You'll see it get mounted right here. Now the media, if you're connecting media up to your machine, like a removable media device, it's going to be referenced here, and your service data will be under SRV. So one thing that's interesting to go on with here is every file in Linux, or everything in Linux is a file. Alright, so now that you've seen this and now that you understand that everything in Linux is a file, even a directory is a file in Linux, which actually makes things a lot easier. You'll see how that goes a little bit more as we go. So right here, we just listed off the different folders here. This is a very standardized version of Linux. We are going to go through some of the history of the Windows operating system, the OS 10 operating system, and we're going to go through the history of the Linux operating system and Unix as part of a further discussion. So that's one thing I wanted you to keep in mind, that none of this is standard, none of this is set in stone. In other words, you could put a configuration file under any one of these folders and it would likely work just fine as long as you have permission to it. This is best practice, and a lot of the stuff that's designed as system programming and system information, it will strictly follow these standards here. So let's look at an actual Linux configuration. So you do have your boot folder, we've discussed that. It's got your proc folder, we've discussed that. There's also a sys folder or directory, which is not on here, so a lot of system files also get run under the sys folder. There's mount, MNT, somewhere it is here, mount, so that's where I could mount other things up. I could mount media. I've got the SRV, there's the user folder, there's the home folder, there's bin, lib, OPT, there is the var folder, the etc folder. Root always has its own home, it seems like, in a lot of these systems. So root, this is the home for root. And then there's dev, which is not development, it's device files, like we've discussed. And we'll get into that, and we'll see that a little bit more later on as well. And then there is the temp folder, which we've also discussed. So this is a pretty good high-level layout here. This is where you'll actually be able to see the different folders in practice. So with that being said, I would like to proceed and go in and show you how things are laid out here. And I've showed you in Windows how the file systems are displayed and what have you. So right here, these are the actual different file systems that you might see on a Linux machine. And this is a very simple setup. This, you can see, it's a small machine here. So this is how the files and file systems are actually laid out in Linux. And don't worry about this command, we will have this later on. Thank you.